Thank you, Bill. So what we're going to talk about is a new way of physically wiring network equipment. So this is the infrastructure that systems that would run InfiniBand or Ethernet, other kinds of protocols would talk to. And what's kind of interesting to me is I've been spending most of the past decade in cloud computing and some background in high-performance computing with woven systems, where I got to know this group, which is why we're here today. There hasn't been a lot of information at the physical layer, and we hope to pique your interest. Some of this is heavily math-based, and we're available to talk to anybody who's interested in a lot more detail after the session. And there's also a fair amount of information on the internet, including a 45-page paper by my co-presenter here, Ratko Tomic. So by way of introduction, to give you an idea, you've seen charts like this, but what's kind of interesting about what's going on in the large cloud data centers is it really mimics what's happened in HPC, because clusters, if you look at the physical topology of what's going on in large data centers, they talk about fat trees, which was unheard of in the large data centers a few years ago. And this is a result of a change in the traffic patterns, because from the early days of web server hosting, a lot of the traffic was kind of described as north-south, where you had access to a website, not a lot of peer-to-peer traffic. But now you see several things going on in the data centers where, one, they're getting a lot bigger, they're using innovative packaging, density's increasing, and it's not going to be uncommon to see 500,000 physical servers in these large data centers, each of which is going to be composed of multi-core processors. And of course, the same processors are being used in high-performance computing clusters. The speeds are going up. And so, particularly with environments running virtualization, you're going to see tens of millions of VMs in these large data centers. And we are now going through a progression. 10 gigabit Ethernet is the pretty typical way people are deploying new servers. There are a few server clusters that are actually being built out, particularly for storage applications today, with 40 gig E. There's some experiments on 100 gig E. And I think you're going to see, I've got another chart that describes a little bit, a lot of progression to speeds as more and more capacity goes. So I mentioned fat trees. So fat trees have become a pretty common way, and some of you in this room know a lot about them. Fat trees are a long way from being perfect. One is congestion really starts to occur when you try to load the fabrics up beyond about 55% with the static routing schemes. And there are a number of reasons for that. And the loads in a lot of data centers tend to have a lot of peaks and valleys. And during the peaks, one of the other problems with fat trees is that you can't take advantage of the non-optimal paths. What do I mean by that? If you look at that picture, if one set of links is loaded up, because of the way they're wired, there isn't a way to take advantage of a non-optimal path. Let me give you a simple example about in a traffic pattern. If you're driving in a car and you hear on the radio that there's an accident, often you may want to get off the freeway and take a non-optimal path in order to do that. Well, the class of topologies that involve rings and hypercubes and so forth, you often have multiple directions that you can take to a destination, a bunch of which are non-optimal. And those are really important in handling what I would call surges of traffic. Another thing that's a problem is that this picture shows a two-stage. It's a fairly simple formula. If you want to define the number of edge ports you can have in a two-stage, it's the number of ports on an individual box squared and divided by 2. So if you have 32 ports per switch, in round numbers, it's about 450 servers that you can connect in a two-stage fat tree. And so if you go beyond 2 stages, these things get particularly complex. And if you build out a data center where you have growth in traffic, when you hit that threshold, you have to do a major recabling exercise to go from 2 to 3. And faster port speeds, as you probably know, mean smaller switches, because the constraint is on the I/O bandwidth of a chip. So, for example, Broadcom has announced they're coming out with a chip this year that supports either about 112 10 gigabit Ethernet connections, different personality of the same chip, supports 32 40 gigabit per second connections. So the other interesting thing is I attended an event called the Ethernet Technology Summit a couple of weeks ago, and a lot of people were talking about 100 gigabit Ethernet and even 400 gigabit Ethernet for data center connectivity. And so if you look at the picture here, the green, this is sort of an eye chart, but the green indicates 100 gigabit connectivity for server connections in the data center. And so it's a few years away, but you're going to see pretty significant adoption of 40 gig connectivity. And so this issue about the number of ports per switch gets to really be a big deal. So everybody talking about cloud computing and networking, particularly in either telecom networking or Ethernet networking, is talking about SDN. So several years ago, this is actually a true story, I was attending a lot of the early sessions done at Stanford, hosted by Nick McEwen, who, as some of you may know, is the champion of OpenFlow and SDN. And I would talk to people about what SDN really was and OpenFlow. And so the way I would describe it, if they had any experience with high-performance computing clusters around InfiniBand, is I said, of course, it's flow-oriented. So that the protocol that they've developed takes into account how to handle flows. But if you can imagine taking a bunch of Ethernet switches, hooking them up with a modified InfiniBand subnet manager, and turning off spanning tree and turning off MAC layering and manually programming the forwarding tables, that's about what OpenFlow is. And yet what's kind of interesting, I had a conversation with Bill Boas when we were talking about whether or not we would get on the agenda, and he remarked about similar observations about early days of SDN. But the interesting thing is it's gotten a lot of publicity, but what a lot of people don't appreciate, it's got no traction. I mean zero traction for data center server connectivity, and it's a very straightforward reason. One, if you take the same layer 2 protocols, such as multi-chassis link aggregation, which is their way of multipathing at layer 2, or ECMP, equal cost multipath routing at layer 3, if you take those same protocols and move them to a controller and use exactly the same switches, there's no cost savings, and at best the performance is the same. So there hasn't really been any innovation in the data center. OpenFlow is a very interesting protocol for other things, but specifically for server networking, it hasn't been adopted. So let's talk about in Infinetics technology, which we've called trademarked long hop, as an alternative to fat trees. And this has in several specific advantages. One is it's a lot less costly and complex when you're talking about networks involving 100 to 1 million switches. And it also has larger bisection bandwidth by up to 3x ratio compared to fat trees. For a given number of edge ports, it also provides fewer interconnect cables. And an interesting phenomena about the Ethernet switches is that you can now buy, as long as you buy them by the pallet, you can buy 64-port 10 gig Ethernet switches for about the same price as you can buy InfiniBand switches today. And in round numbers discounted, it's about $50 per port. And the cost of the cabling in the transceivers now dominates the equation. So if you have to connect with long distance, the transceivers are $100 and up and end. The cables in round numbers, $50 to $100. And so the cable cost and the interconnect cost is a big deal. Long hop has a huge advantage in that, and you can sort of see the ratios here. And as I described it, it's protocol friendly. We've implemented a prototype proof of concept with Ethernet, but it'll work with RDMA, Rocky, InfiniBand, other kinds of technologies. And so with that, I'm going to give you a picture of a long hop network in its simplest form, showing you a bunch of server racks, and I'm going to turn it over to Ratko Tomic.
Hello. Okay, we are now dropping in our layers, networking layers, dropping from all the other talks where you had application layers and then different layers 4, layer 3, and now we are going to layer 1. And the next layer below that is basically math. So, okay. So this is our simplest network, and that was, if you look here how it looks like, it is very symmetrical. You can almost see the algorithm. If you move from one node to another node, you will see that it basically can repeat the rule how the connections are constructed. You skip 2 and then connect, skip 2, connect. So the network looks same from each switch. Now these networks that you are looking here will have direct networks, which means they have, each switch has server port. It's not like factory where you have a core that is just switch to switch connections and then the leaf layer where you have servers. Here each node is a switch, and it has some number of servers depending on your oversubscription. Okay. So now we'll do a little abstraction here. That same network that we just saw is actually this network that's more familiar, probably called folded cube, or it's also been reinvented a few times as bisectional network and some other topologies. The basic construction recipe is you essentially are given, this is regular hypercube, and the first 3 rows in the hop list there, regular hypercube, and the 4th row is the long diagonal. And each digit, binary digit, specifies the coordinate x, y, z. So you can see how these 4 coordinates, and we specify from the root node. And the construction for any other node to see which connection it has, you simply take, for example, shown at 3, you take that node 3 and XOR binary pattern into the hop list here, and obtain the new 4 hops where it goes from node 3. And same thing repeat for all other nodes. So this is general rule for Cayley graphs. This list of 4 hops called generators, and you essentially, that's all you need to have. You have generators, plus you have rule, some operation like permutation or arithmetic rule, how to generate 4 other nodes. In this case, it was just simple XOR of the node number 3 with these 4 hops to get all the target nodes from node 3. And so that's essentially all you have for Cayley graph. You have given hop list, this 4, or it could be more obviously, and the question is now, this particular network has some very interesting properties, which actually was what originally brought us into looking into this. We were looking how to optimize network bisection, latency, and all the nice parameters. And this network does that extremely well. It cuts diameter, basically the maximum path, in half by cutting it across into the farthest node. And but what's more interesting, it also doubles the bisection from the hypercube. If you look, bisection there is n half. For hypercube here is 2 times n half b, that line here. And the bisection is defined essentially, you take a network, split all nodes into... Oh, okay, thank you. Thanks. The bisection is defined, you're probably familiar, it essentially split network into 2 equal halves and count the number of links that cross between the 2 halves. And the bisection is the minimum such cut, the minimum count. So it's the bottleneck of the network. And here we see with folded cube, we essentially double the bisection by just adding 1 link. If you had 10-dimensional hypercube, for example, instead of 3D, you would just add 1 going from 10 to 11 links per node. At the same time, your bisection doubled. With the hypercube to do the same thing, you would need to double the links, which means you would need 20 links per node to double the bisection. And you wouldn't get any advantage in terms of latency. So that was very economical. An original idea was to start with that type of network and move on and see how to generalize this kind of gain. There was obviously some trick to it. And we were looking how, and that's where original name long hop comes from, because the idea was somehow to draw the longest, farthest links at a given time. It turned out that doesn't work. Even for smaller networks, what happens is after the first one is unique, longest in this case. There is single one, and that one turned out to be optimal. But once you go beyond the first one, suddenly you get thousands or hundreds of thousands of equal longest. So how do you do tie breaking? And also what happens is when you add more than few, suddenly you realize that you need to take like this long one, which was good when you were adding the first link, is not good anymore. So it is a combinatorial problem that has exponential complexity. It's not easy to compute. And obviously, if you can't compute bisection, you can't easily optimize it. There are basically two problems: how to compute bisection as accurately as possible, and that is a difficult problem, and then another difficult problem, how to optimize it. So our first step was to try to figure out how to get bisection. And that was essentially, turns out, I'm going to skip some math here, not get into heavy math. I was told in the earlier practice not to go overly in detail, but everything is given in paper, full derivation. Essentially, what turns out that the bisecting cuts, instead of going exponentially, follow. You can use essentially Walsh function patterns to split the network, and one of them will be min cut, one of them will be max cut, which means you can produce minimum and maximum cut of a network by using Walsh function patterns shown there in that matrix of zeros and ones. So if you partition network in n times, so you cut basically complexity from exponential one here over to linear one over here, complexity of the task. So that alone was enough to start playing with this stuff. Once you have, and this is exact bisection you can compute. And with fast Walsh transform, or n log n complexity of that computation. So what happens with that computation, we were able to compute up to a few hundred. Unfortunately, even at that point, trying to optimize that, even though we can compute it now fast and fully accurately, exactly, it was still not good enough. So for about 6-7 months, I played with this, and it sort of kept coming with different algorithms, about a dozen algorithms, and it kept reminding me of something. I said, I've seen this stuff somewhere, but it wasn't clear what it was. It just kept ringing a little bell there. And then suddenly, for some reason, I printed stuff sideways. I was looking, and then I realized what it was. Turns out that problem of bisection, or these cuts or optimization, is exactly same problem as problem of optimizing error correcting codes. So that was the amazing connection that nobody apparently knew about. Okay, we have error correcting codes here given on the right, and you normally, the problem there is you are given input code symbol X, some number, say 4 bits, and the objective is to produce output Y, which is longer than X, has more bits. In this case, it has just parity bit at the bottom. The last bit is just parity. Essentially, the way you compute code word with linear codes is you simply pick wherever X has ones and take those bit columns and XOR them together, and you get column there Y, which is your final output code word. And the number of ones in a code word is called weight of the code word. And the critical parameter in these codes is to maximize the Hamming distance, how many bits they differ in between adjacent code words. Because if they differ, say, in this case, they differ in 2 bits, which means if you disturb any of the single bits in the output Y, you can still recognize that there was error because parity bit will be wrong, for example. Or if you disturb parity bit, you know that some other bit is wrong. In other words, this code is good for detecting a single error because of distance 2. And so the matrix there that was shown with bit columns that you're XORing is called generator matrix. And in coding theory, they put it horizontally usually. That's why I didn't immediately connect what it was. Now, once I realized that this was basically parity check code, then it took several weeks to prove exactly through full math that it is actually true, and it generalizes to all other codes, not just to binary codes, to non-binary codes, to nonlinear codes. And essentially what it makes it, the whole problem of optimizing network throughput is equivalent completely to optimizing the error correcting codes. Now, it just happens that error correcting codes have around since 1940s, and they have tens of thousands of optimum solutions, which means you essentially take this translation recipe, you take hop list H, that corresponds to transposed generator matrix. And these generator matrices you get from the tables, like magma package or whatever, you pull them out of there. And the dimension of the hypercube in this case is equivalent to the symbol length, input symbol length, and the number of topological ports or topological radix m, how many links per switch, topological link is equivalent to code word length n. And the bisection in units n half, you see bisection, lowercase b is bisection in units n half, is exactly same as minimum code word distance. So when you maximize your code word distance, you automatically maximize the bandwidth in terms of bisection. Now, some of the examples here given on the right in a little table of some codes that are familiar, like repetition code corresponds to link aggregation or trunking, which is extremely inefficient. It's one of least efficient error correcting codes, and it's also an inefficient way to do networking that way. The Reed-Muller codes corresponds to multi-partied graphs, and we'll see one in a moment how it looks like. The lowest density of these ends up being like FAT3, direct network version of FAT3 in effect. And the fully connected network corresponds to Hadamard code, which is another interesting code. So this is basically the main recipe. When you essentially take the optimum codes, you get long hop networks. What's not moving? This stopped moving. Did I break it?
Just the arrow keys on the laptop. Yes.
Okay. It's frozen.
Too much math.
Fried the circuits.
More powerful PC.
Yeah.
Okay. What happened?
I don't know.
Okay, go next one. Okay.
There you go.
Okay. Okay. So. Okay. So you get long hop network. Now we're going to look what the effects of that optimization. We basically went out and collected various error correcting codes all the way up to 256 ports, topological ports, and up to million switches. And that covers essentially number of output ports, 117 million. But you can go up to 256. Which is zeta, exa, how many squares you need to do to get to there. So it's basically unlimited. The code tables are huge. And so we basically constructed now that these charts that you'll see now, this pair and the other ones, measure essentially how efficient, how much it improved. In this case, compares long hop versus hypercube. And the red line is hypercube, showing how many ports per switch it yields. And the blue line is the long hop. So at the leftmost edge, hypercube, they use same Radix switches, in this case 64. In this case, hypercube starts off with, on the left scale, is about 7.5 ports, while we yield almost 20 ports. And so on. And the green line is the ratio of the two, and it shows actually that in the range of these sizes, when hypercube goes up to 16 million nodes, it ends up, long hop is as much as 6 times, or close to 6 times more efficient, better yield of ports per switch. That's not just, that means if you're looking for a given number of non-oversubscribed ports, you get that many, you need that much, fewer switches to use, about 5, 6, 4 times, whatever. The lowest one is almost 3 times. If you look at right-hand scale, it's almost 3 times, from 3 to 6 roughly in this range of sizes. And that means also 3 to 6 times lower power on the switches. What, 5 minutes? Okay. So, okay, I need to hurry up then. So another ratio, another table on the right is the cables per port, which shows you even greater ratio, because that combines two effects. combines the fewer switches and fewer cables between switches, so that it's actually the ratios are going between almost 4 and 7 times in the same range of sizes. It turned out, okay, there are a couple on the right-hand side, a little bullet list shows that it has some interesting properties of interesting HPC, which is the largest fault tolerance possible for given number of ports, a maximum number of independent hypercubes as subgraphs of this cube, which means if you are allocating tasks, plus it has another exact graph partitioning in logarithmic n log n time. Another strange benefit that was unexpected was when we designed database, we had bisection optimal and distance optimal for each configuration record, but it turned out that it was almost unnecessary to do distance optimal because they were all optimal to start with. So that was side effect that we didn't expect to come out of it. Long hop versus fat tree. Now we are going to look some of these more advanced topologies beyond the hypercube. Beyond, the fat tree, essentially at the fat tree layer 2, they have same bisection. But once you go beyond fat tree layer 2, already at fat tree layer 3, we are already 1.5 times better in terms of bisection, because fat tree 3 layer and higher are not bisection optimal, unlike fat tree 2 layer. And so it goes up to about 3 times as you go up to size up to 4 million switches. And with ports, it's a little bit larger. Now, one thing with the fat tree is that when you align these two networks that generate same bisections, that fat tree actually on random traffic, which is what you normally would get in your real life usage, is half as good as these direct network like Hypercube or long hop. This is Stanford paper here, and we did a simulation that confirms this type of behavior. And in Stanford paper, they essentially compared the two networks by aligning them on the random traffic performance. And so there is essentially one factor, almost 2, on the chart over there. In addition, if you were to compare. Okay. Okay, now we compared it also to these other networks, and you can see lots of details on these. It's a ratio similar, very large ratios over all the other dragonfly, flattened butterfly, and folded cube. We also have TCALC package, evaluation package, which gives concrete topologies, long hop topologies as connection matrix, and then you can compute, and it shows essentially different parameters, cost per port, normalized to 100 on the, normalized to 100 on the long hop, and 175 that is in switching gear. In cabling, it is from 100 fat trees, 200, and so on. The other networks follow below. And the total and latency also similar from latency, dragonflies right there in the latency. That was their strong point. So they are just equivalent almost to us in latency. With the combined cost, when you normalize everything for your average random traffic, is shown in that cost gigabit per second. So you see that fat tree in that case falls behind dragonfly and flattened butterfly, but they are all 2 to 3 times or even 10 times worse than long hop. If it's $100, and that is not just the switching gear and cabling, that's also the power costs ratios. So it's like having a car engine that runs that much longer per gallon. It's recurrent costs. Okay, and the last two, okay. Another unusual benefit that was not expected was simplicity of cabling. Extremely simple cabling. If you look this as a rack with 32 switches, you can see immediately the pattern. It's almost foolproof. You don't need any table to look or anything to wiring. You can wire it. If you color code it, you can wire it right there out of memory. And what's interesting also with this is that if you imagine that these rows here are not that each row is actually a rack with a bundle of 32 cables, the same pattern holds between the racks, in other words, with the bundles. So that the wiring essentially with 1024 switches, this would give you exact full wiring. So that was low density type network, and the high density one that I mentioned, that a multi-party that's equivalent to FAT3, is this one shown right there. And on the right hand side, this one is essentially like direct network form of the FAT3. And here essentially the routing is also extremely simple on these networks. It shows essentially, we found a very neat algorithm that decomposes the long hop network into interlaced hypercubes. So it's essentially as trivial as hypercubes routing once you have the decomposition. And what we do with that is we essentially we use multipathing and compute all the shortest path for this kind of algorithm between two nodes. And you need to compute everything just for the one single root node, not for every node. Everything is simply symmetrical, and each network looks exactly the same from each node. So what happens, we essentially define for each node, say, 8 aliases or 4 aliases. And then depending which alias you pull, when you're sending at the source, you essentially choose different route. And all these routes are edge disjoint, which means you have full capacity of that many paths between them. And we use static tables to put it in there, and use topological MAC addressing to exceed the limits of normal networks. So we use, for larger networks, we use TCAM and split it into 2 halves, and plus we use IP level. So we have effectively 3-layer topological address, which means you essentially, number of table entries is 3 times cube root of number of switches, of number of servers, which is almost, can fit in pretty much any tables, any size networks. And so that's essentially, and this is our total architecture, how it looks like. When you connect it, we have 2 modes operate, either inside switch or through CLI interface. And essentially there is central controller that computes topology, hands it over, and we have careful division of labor between switches and the servers. So depending in CLI mode, we have to use server-based code. In the switch-based mode, when we have code on the switch, that's this. Oops. There, in that case, we don't need to have anything on the server. Server can be plain server. But if we don't have access to the switch internals, but have to use CLI, then we have to have the server KLM basically on Linux boxes that sits between layer 2 and 3 and intercepts all the layer 3 packets going out, for example, appends the proper layer 2 header and sends it off its way. And so essentially, it's extremely elegant and efficient scheme. It gives you one huge switch, in effect, just using your regular COD switches that can build arbitrary size data center. For example, we looked some case, we would wire, for example, Facebook network, whole big 500,000 server ports, and we take their whole aggregation layer, take whole core layer of switches, take access routers, take that whole layer and just wire the Tor switches that they had, 64-port Tor switches, and instead of oversubscription 150 that they have, you get down to 4 oversubscription. So, and you got rid of half the hardware, all the expensive hardware, essentially in the network. So that's how big gain it is compared to traditional approach.
Okay. Thank you, Ratko. Yeah. With that, we're obviously out of time. I would just like to have the members of the Infinetics team stand up. So we've got several people to talk to here who understand the technology.
It's Chris, he did simulator stuff.
So you can grab any of us. Thank you.